who are my age or older, and who may remember sort of the golden years of Hollywood in the 70s or 80s. I don't quite remember the 70s, but I do remember the 80s. When movies that were sort of big that people watched, they didn't have numbers on the title. Right? That used to be a thing, right? They used to have numbers with titles that are new, movies with titles that are new, right? That used to be a thing, right? That's not a thing anymore, right? So now every movie that comes out has explicit number on the title, meaning that it's a sequel, meaning that it is based on something else, right? You repurpose some old stuff, right? And the reason that's true is has simply economic reasons, right? So the movie business is highly risky. It's very difficult to predict whether a movie is going to make money or not make money. And the median movie loses money. Not the average movie, because then the Hollywood would go to business, but the median movie loses money, right? And the only way the studios can survive is that on the right tail, the blockbuster, that's going to make all the money back. And that's how that's what the big five studios think. Right, so and that's why sometime in the 90s and 2000s, the McKinsey Times sort of decided that the main business way to go is we stop making original movies. We put all the money on safe bets, and that gives us sequels. Iron Man 3, Avengers 4, Transformers 7, and so on. Right, and that's what we do. So for drugs, it's actually the very same phenomenon. Right? So the median drug loses money, and making drugs is a highly expensive, highly risky endeavor because it costs hundreds of millions of dollars. It will, and median you will lose money, right? So what the drug companies do is they try to mediate risk, and mediating risk means doing that innovation. Right? So if you do new crazy stuff and you're gonna put a few $100 million into a crazy idea, then it may not sell, or more likely it may fail and phase 1, 2, or 3, and then you lose money. And that's why sort of the top 8 of the top 10 top 10 drugs in 2014 is similar now. So they're all antibodies or biologics, and the top 3 all at the same time. And now we live in a world of PD-1 or PD-L1 drugs, where the big 4 are like Keytruda, that's called immunotherapy, and there's I think 20 more in the pipeline, and 6 more approved, and everybody's racing to do it. So that's I think one of the reasons that we have little innovation, and that's why we have this sort of drop in productivity. So then the solution. What's the solution? The solution is that ultimately it falls to us as academics to actually because we have this sort of very nice grant-funded, tenured environment where we can do safe innovation, and that I believe is the one. Okay, so what's currently the antibiotic drugs? So the universe of drugs is actually very simple. Obviously, it's all simplified, but so my view of drugs is that there's three types of drugs. Classic drugs. These are enzymes, the metabolic enzymes. There's so-called smart drugs. So this is mostly a cancer perspective, but sort of the only exciting thing going on in cancer therapy now is kinase inhibitors, and so that goes back to the Martinet that was approved in the late 90s, and there's about 30 now. There's a few hundred on the pipeline. That again sort of making the point of the Me Too principle, and the other exciting thing going on now in cancer is biologics, and these target cellular receptors, and there's something like 200 that are either approved or very close to approval, and there's roughly another 800 or so in the pipeline, and ever more. So this is basically what pharma is doing now, and sort of we want to do something else. So there's a bunch of problems with all of these. I'm not going to go into this right now, but there's many problems, but most importantly, we're only targeting a very small fraction of the protein. Right? So there's a few thousand. So there's actually only a few hundred targetable receptors with antibodies. There's there's a few hundred kinases, a few hundred enzymes. So we're only targeting less than 10% of what we could target that protein with Okay, so what we do, what I want to do is I want to do something new. Understand? We want to innovate, and then what we're doing is we want to find new target classes. And so I'm gonna talk about 3 types of target classes. So the first one, that's my favorite one. So we have about 100,000. We have a few 100,000 of protein-protein interactions in the human proteome. It's the exact number is still debated, but let's say it's 500,000. There is now there's one drug target that was approved last year. It's called the UofT venetoclax. It's approved for leukemia. So in theory we have a few 100,000 more protein-protein interactions that we could use for therapeutic intervention. But then the next one, and that's my other favorite one, we have transcription factors. So there's over 1,000. There's something like 1,200, that like 50. I think the number is not right, but there's like over 1,000 transcription factors in the human proteome. There are no drugs to transcription factors. 0. There are some nuclear receptors, but I would argue there are receptors for transcription factors. But so and for transcription factors. Obviously, they're important. They regulate gene expression. Well, presumably, that's pretty important, right? So, but there's not a single drug, right? And the other important thing is that there's many well-known ones that are oncogenic, NIC, NCOB, ETS ERK, Phos, right? But we haven't figured out how to inhibit this. Right? So that's what we want to do. And finally, so going back to the outer membrane. So most of the membrane proteins are very difficult to target because they're integral membrane proteins. So current antibodies only target receptors that have a full extracellular domain that you can cut off in the pure form, right? Because membrane proteins are difficult to make. Okay, so these are the 3 areas we're playing in. Let's now focus on the first area. That's protein-protein interactions. Okay, so first we have a problem. I mean, so there's a reason why big pharma is doing this, right? And the main reason goes back to that notion that protein-protein interactions are what they call undruggable, right? So that's an example of protein-protein interaction, and so medicinal chemists would go and would say that's crazy, right? You can't make a small molecule drug that'll somewhat fit there and breaks this, right? It's too large, too flat, so you won't find it. So that's why PPIs, I think back in the 80s or 90s, they got this reputation of being undruggable. So that's not quite true, and that's something I've spent a fair amount of my career studying. Is that we have a continuum of protein-protein interactions. So we have domain-domain interactions that look like I just described. But we also have, and that may not even be the minority, we have domain motif interactions, where you have a protein binding to its target, by virtue of a short peptide motif, right? And then you can see here that you have some sort of cleft here, right? And it is much more easy to imagine a drug-like molecule actually binding to this cleft and doing something. And here's another example. Right? So it's not flat. It's much more what we would call druggable. So the other good news is, and we have one portion that's called a third of PPIs that are druggable. The other good news is that these motifs here, they're pretty easy to identify from the sequence. Right? So we know where they are. Right, so and Alan Moses and the people in this department have done a lot of great work on this, right? So he said he won't be here, but he said some of his guys are here, right? Maybe they're nodding. So we know where to find them, right? And then we can use these motifs to find inhibitors, right? And as an aside, so back in the 80s. Back in the 80s, the kinases had the same reputation of being undruggable, right? And that's obviously changed, right? Now everybody and his brother wants to make another kinase inhibitor, but that used to be different. So And some people may argue that PPIs may be the next kind of business. So the big success story here in PPIs is BCL2-BH3. So that's BCL2, and the its interaction with BH3 is mediated by this short peptide. This is the peptide. This is part of what you can cut that out of BH3, and then it'll bind here, and it'll dislodge the native protein BH3 from the spot. And people first recognized that cutting out this peptide and making it would lead to apoptosis, right? And would then kill cancer cells. And then in a relatively long story, they went from this peptide to Tyromatic. That was largely a Genentech project and collaborated with Abbott. And that was now, and as I said, this was now approved last year as another drug named Venetoclax, and it is now given to patients of chronic lymphocytic leukemia. Okay, so this stuff does work, right? So it works. It's in the clinic. It helps the 10 patients, right? But it's only worked for one case. So we want to do it for many cases. Okay, so how do we do this? So what we want to do is we want to generate a library of compounds that can target all possible protein-bone interactions in the proteome. Right, so we wanted to generate a library of a few 100,000 specific protein-bone interaction inhibitors, and we screen the interactome, and then each inhibitor is going to go and break one interaction, and then we can observe the phenotype of what happens. Right? And then we can presumably fish out the ones that do what we want them to do. Okay, so we do that by, as I said, first we take the human proteome, we identify the potential motifs, which methods such as the one that most discovered, and then we get a library of roughly 500,000 phosphopeptides, right? And then we can make this. And this is an old slide, but by now this is something we do routine. But 3 years ago, this wasn't so routine. So basically, what you can do now is you can get these synthesized on oligonucleotides, and you can clone them wherever you want to, and the neural life is going to turn these oligonucleotide peptides for you. Right? We are its customer. Okay, so that's the way it works. So we start with a network of protein interactions. We generate this library, about 500,000 peptides. We have it synthesized in oligos, and then we clone it into a lentiviral vector. And then what happens? We can take this lentiviral library, where you have 500,000 lentiviruses, each one corresponding to one peptide. You can use the lentiviral library. Skip that. You can use the lentiviral library to infect a cell culture, and then in the cell culture, roughly every cell will be infected by one lentivirus, and this cell will then express one peptide, and then this peptide will then inhibit the interaction it's supposed to inhibit. So the peptide is going to inhibit this is going to inhibit this, and then you can follow the cell culture over a time course, and you can observe its phenotype. And in this case, the phenotype we observe for is just survivability. And so the idea here is that because the peptide is going to be expressed only in its own cell, and when the cell dies, the cell is gone, and we can't see the cell genome anymore. So this is how we have to link between the phenotype, the peptide, and the genotype. It's sequence of the peptide in the genome, put there with lentivirus. So then we can follow the time course by simply high-throughput sequencing the barcode, and the barcode is just the peptide. So and then we get the barcode time course here, and we can plot it, right? And then presumably what you want is you want a peptide inhibitor that will kill your cancer cell like this, and we use some sort of control cell, and it will kill it. It won't kill it. Right? So we do the experiment simultaneously control cell and the cancer cell, and then you can come up with a score. But really you can sort of plot these and then follow the time course and identify the inhibitor that does what you want it to do. And you can do that, and then lo and behold, we get peptides that indeed do this. We also get peptides that are just generally toxic, right? Okay, so interestingly, one of our top hits, not the top one, but in the top 5, is the famous peptide that inhibits the MDM2 PVC interaction, right? And this peptide that was made by a company called Cellular Therapeutics. It's a stable peptide now, and that's now in phase 2 in the clinic. But that went to phase 2 like a couple of years ago. I haven't quite. I don't know. They haven't published their findings, which I don't know. Might mean that they're not good. But anyways, it's in the clinic. It's being given to real people. Okay, so then we can validate this in single antivirus experiments. And indeed, we find peptides that have reasonably strong effects in so-called cancer in cancer-derived cell lines, and have much less of an effect in so-called normal cells. Okay, so we did the screen where we identified a bunch of peptides that do what presumably we want them to do, i.e., killing some cell line, not the other. So now we have to identify their targets. Right? And we do that by sort of a mixture of computational techniques, using structural models from the PDB, and using some protein-protein interaction databases. From the structural sense, you can simply map the peptides to known protein-protein interaction complex structures, and then find matches. Right? So if it works very well. So in the cases where it does work, we find very good hits, and this is how we find this one here, or the p53 peptide here, or the GNG4 one here. It doesn't work because the structural coverage of interactions is still relatively low in the PDB. It doesn't unfortunately work for all the many cases, but when it works very well. An alternative approach is to make use of known databases, and we use back then we used a mixture of Biogroup P5 and Elm, and this is how we found this instant peptide, which we're following up, and then another one called Cosmos 81 that I launched this year. Okay, so then we found the peptides that do what we want. We found some of the targets. So now we have to validate that indeed these peptides do work to the targets we think they do, and we do that by doing a fairly basic array of techniques. So this is the peptide we selected. So the first thing we can do is we can simply do pull downs, right? Do flank AGA pull downs. Basically, we put in the target interaction. That's protein A, protein B. And then we transfect the peptide linked to GFP, and then in theory the peptide would then bind to the target and would displace the protein. And we do indeed see the working in these cases here. Right? You can see the HA band appears and the GFP band appears. So showing that a peptide binds and that it indeed displays the target. So that does work in these couple of cases. We can also play some more games, and we can show the threat that a peptide in vivo-ish in cells binds to the target, right? And you can see that here. We get some nice vesicles here where clearly we're binding of the peptide to the target. So the stuff that works. And this is a little complicated. Let me skip that for okay. So finally, you have to figure out what actually happens. So why does this peptide actually kill gamma cells? And so this is of course case by case specific. So we only followed up a few cases. So one case that's pretty easy to understand is the MDM2 p53 case. So MDM2 is, as you may or may not know, that's an E3 ubiquitin ligase, right? So it puts ubiquitin to its targets. And when you break the interaction between MDM2 and p53, then p53 will no longer get ubiquitinated, and it won't be degraded. Right? So that means that the p53 levels go up. That means p21 levels go down, and that means you get apoptosis. Right? And if we follow that in gels, we indeed find that with peptide you get higher p53 levels, and actually high activity levels, and then apoptosis. Another case is with the SFN interaction. Our hypothesis was that this leads to inhibition of cyclin B1, which would lead to cell cycle arrest. And we tested this, and indeed we find through faxing we find cycle arrest in GT by transaction peptide. So that's at least consistent with the hypothesis. Okay. So I promised you, I told you that we want to put stuff in the clinic, which by the way we're a very very long way away from still, but we're working. So so peptides are of course terrible drugs, right? And most people know this. So there's a number of problems, right? So the one problem is they're fairly degradation prone because the proteases are swimming around in the blood. We have relatively low affinity, and we, in general, I don't show the data here, but we generally find affinities in the low micromolar range, which is not quite tight enough to be pharmaceutically viable, because you don't want to inject yourself with tens of grams of peptide, right? And the most difficult part is that peptides generally don't cross the cell membrane. So there's exceptions, but generally don't. Okay, so there's various solutions to this, and I'll go through some of the ones that we found that we do. So to address the affinity, we make use of a computational pipeline we developed, and that involves we make all single mutants, but we also use non-canonical amino acids. So the idea being that canonical amino acids is 20, non-canonical is about 200 that are commercially available. So you increase your space by tenfold. Right? So you make it much more likely to get something tight. So we do some sort of coarse-grained scoring with a cheap energy function from Cellular. That's quick and dirty, and then we narrow it down to maybe 50 or so candidates that we test with a more complicated calculation called TI, similar integration. That's very expensive, but luckily, so thanks to computer games, this is actually much faster now, right? Because now, and that was a big revelation to me a few years ago, that with modern graphics cards, GPUs that some of you may use in your computer to play. I don't know. What do kids play these days? I don't know. That was Quake in my day. Anyway, so with these cards, our computational power increased about 100-fold or so. That's enough to be transformative, right? So one of these calculations would take weeks. Now we can do it in a day, right? And then we do some manual inspection, and we select the best candidates. And with this, we find we can. So in one of the cases, we can improve our apparent efficacy, or our apparent potency in cells, from about 2 micromolar to just below 1 micromolar. Right? So that's pretty good. We're still not quite where we want to be, but it's pretty good. Okay, so then we wanna the main problem is, oh, by the way, so these non-canonicals, they also address the stability issue, because non-canonical amino acids aren't recognized by the proteases, right? So then finally we want to address the cell delivery issue, and that's the most complex issue. But so it's a very active area of research, right, or engineering, I should say. And there's, because everybody wants to make intracellular biologics, so it's very difficult, right? And so there's this stable of different techniques that people use. So we personally tried 2. So we tried the 2 that make sense to me, right? So the other ones don't make sense to me for various reasons, right? I mean, still peptide CPPs, that's just plain magic. Secret peptide is too complicated. Nanoparticles go to the liver and to the skin, but not necessarily other places, right? So we tried the 2 that make sense to me. Okay, so also the 2. So the first one is delivery with anthrax toxin. That sounds scary, but it's not that scary. So the idea is that So anthrax toxin consists of 3 parts. Actually, only 2 parts, but let's call it 3. So you have the elephant protein here, and you have this poor protein that's called PA, the anthrax protective antigen. And usually what anthrax does is it goes to your, so these things go to your epithelial cells. This whole thing is endositized, and then this pore together with your N gets injected into your cytoplasm. And then this thing here is the anthrax toxin. Right? And the toxin, then this is the actual toxin. This will kill you. Right? So what we do is we chop off the toxin. And instead of the toxin, we put a peptide there, right? And then this bond gets cleaved in the cytoplasm, right? So then you end up with a peptide in the cytoplasm. So that's we didn't develop this. This is developed by Brad Panther at MIT, and so we collaborate with him, and we do get fairly good uptake. This is staining for antibody staining, so we get fairly good uptake of our peptides in the cytoplasm with the system, and phenotypically we get about single-digit micromolar IC50s of cell killing in the system. So this does work. We also tried lipidation. So there the idea is that if you have a somewhat greasy and not too charged peptide or not a negatively charged peptide, it may enter the cytoplasm if you stick some more grease onto it, right? And we do lipidation with palm oil, and then indeed we do see fairly good effect on cell viability, and if you label them, we do see pretty good uptake. So it does. Okay, we will be able to. Okay, so to summarize, so we're still working hard on bringing forward some of these things, and we're still hopefully in my dreams or in my plan we'll get some peptide into animals hopefully next year or so. So to summarize this part of the talk, so we established this new technology platform, and we identified a number of promising leads for cancer therapy. So we're now moving forward, and as I said, in trying to develop these into hopefully someday viable drug candidates. But I can tell you that that's a very long slog that we've been on now. So we're now we're still very excited. So what I'm very excited about now, I just started a new collaboration where we apply the same platform to neurodegenerative diseases. So Parkinson's or Alzheimer's. So Parkinson's, Alzheimer's, there's people are very desperate because cancer. Quite frankly, cancer. People are not that desperate because there's actually a lot of cancer drugs out there and in the pipeline. But Parkinson's, Alzheimer's, there isn't really anything credible out there yet. And so we're starting a project now. We just did the first screen in Parkinson's, and also it makes the screening much easier, right? Because in Parkinson's, in these things, you want to keep neurons alive, neurons dying, right? And if you screen, it's always easy to screen for stuff that keeps stuff alive, right? That kills stuff. So we're doing that. Okay. So okay. Let me see how many time. Okay. So I'll go to the second part quite quickly. I talked in the beginning a lot about antibodies, right, and about biologics. So just to remind you, that's antibodies. That's the thing. So antibodies as drugs. That's a big thing. That's like a $30 billion worth of thing. So as I said, that's the main thing. And about half of these today, about half of these are generated by a technique, by some version of randomization and affinity screening. It can be phage or yeast display or ribosome display or any of the other smart displays that people have developed. Phage display is the main one. But so basically most of them are developed by, you take a scaffold of an antibody, you randomize stuff, and then you screen, and then you get something. Right? So that's basically how these are made. Just as an aside. So there's many problems with this, but as I said, there's people at all the drug companies and all the biotech companies that do this every day lots, right? And on our campus, of course, there's Cellular, who is a gigantic operation, basically for people who basically do this stuff, right? Okay, so I thought being coming from structural protein background, we can maybe do something. So the intellectually, or the dirty little secret of protein modeling is that quite frankly we sort of lost the battle in some sense, right? So trying to get a protein stick to another protein, right? That's what we call protein design. That's one version of the protein design problem, right? That's something that intellectually we should be able to do. Right? Intellectually, we know so much about proteins. Like we have incredibly powerful computers. Right? We have 4 decades worth of data on structures. Right? In theory, if somebody only gives you this task, you have a scaffold, and you want to make a variant of the scaffold that binds there tightly. In theory, you should be able to do this, right? And so the answer is we're not. Right? So basically this battle between computers and combinatorial screening, and so we lost at that. Right? So these guys are much better at this than we are. Right? That's just ambition, right? But still we still know stuff about proteins. Right? We have 4 decades worth of data. We have very powerful computers. We have big data and deep learning and whatever. Right? So maybe doing this brute force approach, where basically you forget everything you know about proteins and you just test very big libraries, maybe that's not the best way to go. Right? So maybe there's some room for all these powerful computers and for all the stuff we know about proteins. Right? So that's what I set out to do. So our approach is we use computational design. We design our variants, and instead of randomizing them, we design them all on a computer. Right? So every one of our variants, the computer has looked at and has decided that is good. The computer isn't that good at it, but it's probably better than random, right? So then we can synthesize these, and we can make use of the same trick as I took in my first part of the talk by using oligonucleotide synthesis. We can synthesize all of these, and then we get a few hundred thousand, maybe up to 1 million determinedly designed sequences. They're not random at all. Every one the computer has said these are good. We can do the same sort of thing. So we can do something with phage, bacterial hybrid, yeast hybrid, mammalian systems, and whatever. Right? Okay, so that's what I set out a couple years ago, and that's what we do. Okay, so there's a couple of important advantages here. So one advantage is that by using this computational design, you get to decide where your binder is going to bind. Right? Okay, you can say you're going to bind here, and you're going to bind in this conformation A. Right? If you use a randomized technique, then the thing is going to bind somewhere. Right? You can't control where it's going to bind, and you can't control which conformation is going to bind. It's very difficult for the phage guys to get you agonists or antagonists. I mean, you don't want just binders. You want something that does something if you want to control, right? So this is something we can ensure. And the second advantage is that by having much smaller libraries, we can select in cells, in mammalian cells, and that sidesteps the very large problem of having to purify the target protein, because purifying protein is hard, especially if it's membrane proteins, which are, quite frankly, most of the drugs most of the targets that we're interested in. Okay, so this is how it works. So this is a pipeline as we designed it a few years ago. So we take our scaffold, we take our scaffold and our target. We generate a backbone ensemble with 2 different methods, with ND and with a harmonic oscillator based method called Concord. Then we get a backbone ensemble, and we also use, because as I said, my student Mark's son, he's a computer science student, so he wanted to do something more machine learning-y, and so we devised a machine learning-based process called Gaussian process with latent variable modeling. And then we generate these backbones, and each of these backbones we perform fairly standard protein design, so Rodimer-based, MCMC-based protein design, and then we generate sequences. We get this synthesized on a DNA microarray, we amplify it, and in the case we published it, we put it into phage in the yeast hybrid library, and then we can screen it with the feature describe it, and identify binders with deep sequencing. So now we screen also bacterial cells and mammalian cells with different collaborators. Okay, so how we generate vector ensembles is relatively simple. As a Concord is an Oster-based methods that basically lets that protein wiggle as a spring, as a balls and springs kind of model. You have MD where you can basically let this wiggle in solution. There's a backdrop, sort of a rotation-based methods, and again the one we invented is based on existing structures. So if most proteins have more than one structure in the PDB, right? So some have up to hundreds. So you can feed this into a machine learning model, and it'll learn realistic motions from the structure. People never call me. Anyways, okay. So just to show that this works, so we applied this to a system from one of my colleagues, the UofT21 ubiquitin system. So the wild-type ubiquitin that we designed to stretch here, wild-type ubiquitin has some very low affinity to the USP. You can do conventional phage display, and so the people who are the best at it in the world, they get a 20 nanomolar binder with a 10 billion library. So when we do it with a very small library of S binders, it's about 10-fold tighter. Okay, so it does work, and again, we didn't do this here, but we could, because our library is comparatively tiny, so we could screen mammalian cells, which we actually do. And we can confirm that LKB is that low with ITC. So then we can play some games with sequencing counts, and because in theory, sequencing counts in these experiments are strongly correlated with affinities. So we can show that here, right? That here we have IC50s, which are more affinities. We can show that they correlate very strongly with our sequencing counts, and then we can generate based off of this we can generate an oracle that will a random forest oracle that will predict affinity just based on sequence structure features, right? Whereas the original Rosetta energy function. The original Rosetta energy function actually correlates fairly poorly with affinities, but I should say that all the ones, almost all the ones that we put out, that we designed, were lower than about 70 nanomolar. Meaning that the Rosetta energy function is probably not terrible at getting you stuff, at getting you binders that are medium affinity. It's reasonably good at sorting the garbage from the not bad. It's just really bad at sorting the not bad from the good. Okay, so we can use it now. Okay, so now we built the single logic, and we're now in application mode. So we're applying this now to the cell-based selections against UPCRs, which people care about. We're doing selections now against transcription factors, and we indeed we do have binders. We do have inhibitors of transcription factors, which is pretty cool. Okay, this is my lab from a few years ago. This work is largely the work by Satra and Claire, who's left the lab now. Did most of the peptide screening work. So Satra did most of the screening, and Claire did the analysis. And Moon and Mark did most of the work on the protein design and the screening. And this is the collaborators, and this is my funders. And thank you for your attention.
Any questions for Philip? Over at the back.
So very nice talk and very timely. We have wide open horizons in front of you in the drug discovery. And two questions. So in your lentiviral peptide screen, did you come across nucleoproteins? I mean, p53 MDM2 shuttles, but I mean your peptides don't probably get directed to the nucleus. And then second question is, when you talked about about the QDs and just being in sort of micromolar range, I mean, this is a long evolutionary process where you take protein and then you try to find a peptide. Do you think something is missing peptide because there's an interdomain? I mean, those slow QDs are puzzling to me.
Okay, so very good questions. Thank you. So the first question, so that's a very good observation. Yeah. So I guess you're very right that so in theory our peptides should only be in the cytoplasm, right? And indeed, so most of the things we do fish out up cytoplasmic targets. So we have found some that look like they should be active against nuclear proteins, and we did some localization assays where we do find some evidence that they are indeed in the nucleus. But that's a little. I mean, I would argue that's a little weird. So I would agree with that. So we tend to only follow up on cytoplasmic stuff for now. So now that we do transcription factor, with these things we put an NLS there on purpose that goes to the nucleus, but we don't have any NLS at that time. So that's a very good point. On the second point, there definitely are peptides that bind nanomolar affinity to their targets, right? But philosophically, you could argue, and many people do, could argue that this is only because the target evolved to bind the peptide so tightly, because you need like a very nice pocket to like grab the peptide and get sort of off rates that would give you a nanomolar affinity. So I'm still optimistic that with at least a portion of our targets we will get to the nanomolar range. Simply because if you look at some of our structures, then it simply seems like sort of this cleft would have enough room for improvement to get down to nanomolar. But having said that, we've been so screening is easy and it's fast, right? And follow up takes long. So we haven't on it now for over a year. We haven't got the nanomolar affinity. But I remain optimistic. As a scientist, I'm a born optimist. So I remain optimistic we'll get there.
Yeah, along the same lines, do you find that during your screens that many of your peptides are just toxic to the cell because they aggregate or they muck up the proteasome and put stress on the cell, which would be not directed towards a specific target, would be a non-specific effect, toxicity?
Yeah, no, you're right. So definitely there's a whole group of peptides which are just generally toxic. Right? We find, in fact, many of them, right? Because we are expressing a lot of peptides in the cell. To be honest, we never actually followed up on them. We probably should.
I suppose they'd be toxic to your control cells as well.
Yes. So that's misunderstood. So we definitely find that. I mean, now that you say, we should probably follow up on this. We just never did. But because my bandwidth isn't that big, so
I'm just curious about well, two things. One is, for example, can your peptides differentiate between wild type and a mutant oncogenic protein, for example, p53? And in terms of the context of doing it in vivo, can you have you assayed primary cells alongside your cell lines to see if it still has activity in primary cells or doesn't have activity?
Yeah, so that's an excellent point. So the first point, that's also something I wanna get to. That doing more specific screens and or assays for specific mutants or known oncogenic mutations, as you say. We still haven't gotten there yet. So the one issue is that with peptides you may have more limited specificity. So I'm more optimistic for that with sort of full-on biologics, with a full-on antibody or other larger scaffold where you have you know, a lot of more information in a large surface area where you can distinguish between you know, two proteins that only differ in one or two amino acids. But I definitely want to do that. For your second point, yeah, with primary cell, that's a very good point too. That also we haven't done yet. You know, we definitely want to do that. We just haven't gotten there. Yes.
Two questions related to the size of the peptides. Does the size of the peptide relate to the ability to stabilize them and make them cell penetrant or not? And how does the distribution size of the source library compare with the peptide that are hitting at the producer phenotype?
So that's another very good point. You know, membrane permeability of peptides, it's pretty astonishing with this. But there's relatively little known sort of systematically. So anecdotally, people think that shorter peptides have higher permeability, but there's surprisingly little systematic evidence for that. But that's what people think. So you can argue two ways. So one way you can argue is, and that's, I'm not sure I like this way, but anyway, so one way you can argue is that there's one way to go in is just permeate passively, right? Basically be a small molecule, right? And once you violate any of these rules, so that's the Lipinski-5 rules, right? Once you violate this sort of physicochemical space, then you know, uptake won't be passive anymore. You won't be able to permeate, and then the size doesn't matter, right? So once you're, and for basically no peptide that we make, so anything bigger than 2 or 3 amino acids won't permeate by itself, right? And then you have active uptake, and then it doesn't matter whether it's you know, 10, 20, or 20, right? So that's one way to argue that you know, a lot of people make that argument. Other people still argue that you know that shorter peptides are easier for uptake because you have vesicles forming, and maybe it's too big, it won't fit in the vesicle anymore, or there's other sort of things going on. But to be honest, as I said, there's you know, disappointing or surprisingly little is known about this, given how important it is for the industry right now. So we're basically in just engineering mode. Basically, we're trying stuff, and if it works, it works.
So I had a question about off-target screens.
Yes.
Maybe incorporating that into your pipeline. You know, I've been familiar with some of these, you know, using CRISPR screens or mutagenesis screens to try to identify targets, and I wonder if you could use that to really try to assess specificity. You have great on-target assays, but you know, in terms of trying to find out what other targets there might be in the proteome.
Yeah, so we do that a tiny bit. So we did that a tiny bit, and that was just on the cusp of the CRISPR era. So we did RNAi. You know, now you would CRISPR, of course. So we did that in the sense of that you can knock out your target gene, and then put the peptide in. And then presumably your peptide won't have an effect. Yes. Right. And so we did that. That's one way of doing it. I still haven't set up CRISPR on that. I probably should, but it's something that we just haven't gotten around to.
All right. If there are no more questions, let's thank Philip again.
Thank you.